Okay, so good evening, guys. My name is Devadun Banerjee. I'm a PMRF PhD scholar of Indian Institute of Technology, Delhi, and I have a live session on this particular NPTEL course named as Waste to Energy Conversion, and this is live session number 2. So basically, in this week, the first lecture was covered on basically some tutorial problems. So one such problem is to determine the water equivalent of a bomb calorimeter 0.1651 gram benzoic acid sample having an higher heating value of 6318 calorie per gram was used. The experiment produced a net corrected temperature rise of 3.077 degrees Celsius. The acid titration required 11.9 ml of standard alkali and 8 centimeter of par 45C10 nickel chromium fuse wire was consumed in the firing. So you have to read the bomb calorimeter. Okay, so let us see the solution. Basically, it's a simple problem. Actually, this kind of one problem was also discussed in the last session also. So the given data basically are the high rating value, the benzoic acid sample utilized, values are given also. So you have to keep in mind this particular formula to determine the water equivalent, which is H into M, that's high rating value, and multiplied by the benzoic acid sample titration which was used. Okay, and plus E1 plus E2 plus E3. What is E1? E1 is you have to multiply the titration value of the standard alkali is 11.9 and the value, okay, the 1 calorie per ml. That particular value you have to multiply, so we'll get the 11.9 calorie. E2 have to get that 13.7 into C2, and E3 will be getting 2.3 into C3. C3 is given 8 centimeter. So you have to just put the values, and temperature rise is given about 3.077 degrees Celsius. So it will come around 2402.1 calorie per degree Celsius. It's just if you don't understand, just go. I think lecture 3 or 4, you'll get the detailed things. So another problem, 1 gram of an MSW sample is heated at 105 degrees Celsius for 24 hours, and the weight of the dried material is found to be 0.8 gram. which is further heated in a furnace at 950 degrees Celsius for 7 minutes in the absence of air by putting the lid of the crucible. The weight loss is found as 0.4 grams. The lid cover. When the temperature reaches the ambient temperature, its lid is opened and is further heated in an oven at 750 degrees Celsius for half an hour in presence of oxygen. After cooling the material, the residual mass of the material is found to be 0.12 grams. So, I have to determine the moisture content, volatile matter content, ash content, and fixed carbon of the waste. Very simple problem from the from the options you can just tell the answer. So, does anyone get the answer? Let us see the answer then. So, it's a very simple, straightforward problem for about approximate analysis. So, see that in the first statement, 1 gram of the is heated at 105 degrees Celsius for 24 hours, and the weight of the material, dried material, is 0.8 grams. It means then 0.2 grams were removed, and 105 degrees Celsius for 24-hour heating means we basically removing the moisture. So moisture is 1 minus 0.8, 0.2 grams, which is 20%. Straightforward thing. The second option is told that 950 degrees Celsius heating for 7 minutes in absence of air by putting the lid of the crucible, 0.4 grams. So directly if total is 1 gram, 0.4 gram loss, so it means 40%. And this particular procedure for 950 degrees Celsius for 7-minute heating in absence of air is carried out to determine the VM percentage, volatile matter percentage. And the last one, 750 degrees Celsius heating for half an hour in presence of oxygen. Which means that we need to do the combustion in presence of oxygen at 750 degrees Celsius for half an hour. And the residual mass was simply 0.12 upon 1 means 12%. And the rest, if you just sum them up, 0.8 plus sorry 0.2 plus 0.4 plus 0.12 and subtract from 1, we'll get about 0.28 grams, which means that 28% is fixed carbon. Okay. Another question is sample problem. COD analysis of a wastewater sample is carried out through a chemical method using 10 potassium dichromate solution as a reducing agent. Excess dichromate is titrated against ferrous ammonium sulfate. 150 ml of wastewater sample is used. The titer value of ferrous ammonium sulfate are 55 ml and 75 ml for the original sample and blank sample respectively. Determine the COD of the sample. And these are the four options. Okay, so let us see the solution. So COD you have to determine by this particular formula, uh, which is 8 over 3 into B minus S into N divided by sample volume. What are these B, S and N? B is the volume of the ferrous ammonium sulfate used in the blank sample, and S is the volume of the ferrous ammonium sulfate in the original sample, and N is the normality of the ferrous ammonium sulfate is used to determine the COD. Okay, there will be a kind of long derivation of this particular COD. You can check that if you are interested further. So just put your values. So B minus A here for the blank sample, and original sample you get the 55 into N. N is a normality, which means N by 10, which means 0.1, and sample volume is given 150 ml of a starter sample. So divided by 150, you'll get directly 106.66 mg per liter. The answer of the COD analysis. So lecture 1 basically covered this kind. Some more problems were also discussed. You can check that, or if uh, you can check that, they will be also very important for the examination and assignment purpose. So we come to the lecture 2 and 3. It covered basically the details of the incineration. So the contents were the definition and scope for application, the mechanism of incineration, air requirement in incineration, the performance factors and staged combustion, its advantages and disadvantages, different feedstock preference. This was mainly in the lecture 2. Let us see a bit. So in the incinerator, basically you give the waste in the presence of air. It gets basically combusted. Some output gas is actually released in the form of CO2, H2O, NOx and SOx, etc. And because of the combustion, some this we obtain ash also, right? So the output gas can be used for heat application or electricity production. The volume of the waste is actually gets reduced. Obviously, if you just incinerate it in the presence of air or oxygen, the waste, actually this kind of waste amount would be reduced, but obviously not nullified. Okay, so it can happen via basically heating and drying, the pyrolysis method, and the char and volatile gases combustion process. So heating and drying is normal basically when in the presence of heat the moisture removes. So basically the sample gets dried. So if you heat above the 100 degrees Celsius, which is the boiling point of water, you get the moisture removed. Pyrolysis. So in the presence of basically a kind of an inert atmosphere, basically if you give the air about is there. So some portion of the pyrolysis is also occurred, and in pyrolysis what happens is some volatile gases, they actually come out in the form of CO, CO2, H2, H2O, like that. Okay, and finally the char combustion, which is shown here by the shrinking core model. So what happens is when this oxygen of this particular air, about 21% oxygen is there. So when oxygen to penetrate the sample from the outer spot to the inner core. So gradually the core basically gets shrunk. Okay, so and how why it is shrunk? Because the loosely uh, attached particles and also the combustible material, also the volatile material, though they come out, and they form some this kind of gases. The solid material, the solid core material, this diameter gets gradually reduced, and this is actually represented in the form of a shrinking core model. So complete combustion will occur when proper amounts of fuel and air are mixed for the correct amount of time under appropriate conditions of turbulence and temperature. Basically, fuel to air ratio, thereby you will achieve the complete combustion. And so for that you need to know the basic stoichiometry of the reaction, and for that you need to know the basic chemical formula of your waste, and that is why the initially the proximate and ultimate analysis are needs to be done for a particular waste sample. From that you will get to know the composition, and that by that composition you will get to know your how much the stoichiometry, and you supply some excess air than that, because obviously nothing is 100% efficient in practical, right? So beyond some excess air you supply, so that you try to minimize the incomplete combustion, because incomplete combustion you'll get some poisonous gases like CO, or maybe some portion of methane, or some other kind of NOx, and all those things are also formed by incomplete combustion, especially mainly CO, because carbon is a big important waste material. So to remove that particular, to minimize the probability of formation of this kind of CO by incomplete combustion, we give the uh, sufficient amount of air, in especially some portion more than the stoichiometric requirement. Okay, that is the thing which is written here. The percentage of excess air, which means is the amount of air above the stoichiometric requirement for complete burning. The in the incoming air not used during the combustion is related to percentage excess air. Typical excess air required for various combustion systems is in the range of 5 to 50%, depending on the fuel characteristics and the system configuration. Successful combustion of solid waste is accomplished by controlling the three T's of combustion: time, temperature, and turbulence. So, how time is important? The period taken for solid waste to pass from charging hopper until the bottom ash is subsystem. So the time is actually very important and performance factor. So usually 45 to 60 minutes time is typical time for particular this combustion in an incinerator. Sorry, yeah. So the apart from time, temperature is also an important factor. So the usual temperature, which is which 180 degrees Celsius, close to 1000 degrees Celsius within the furnace, and is directly proportional to the residence time. If there is insufficient time is in the furnace, the combustion reaction cannot proceed to completion and the temperature declines. Because of the exothermicity of this particular reaction, the combustion, the temperature gets usually increased. So if the complete combustion does not happen, so the temperature gets decreased. So these are the some kind of the performance parameter, performance factor which. So the staged combustion, that is why is carried out to achieve enhanced combustion. The primary air injection is made in the fuel bed, and secondary air injection is made in the combustion chamber. Okay. So this enables good mixing of the combustion air with the combustible gases formed by devolatilization of the fuel bed. So two times basically the air is injected, an insurance of the complete combustion. So firstly, the first air injection is made in the fuel bed itself, in the fuel, the portion, and the secondary air injection is made in the directly in the combustion, so that when that particular fuel bed is actually moved towards the combustion chamber, it gets completely combusted, and it it gets connected. excess air uh, environment, so that no chance of incomplete combustion happens. Okay. So and also another important thing is that uh, uh, so you have to think about the economy also, right? The economic efficiency. So the uh, low excess air is also that is why an important factor. So the excess than 1.5 times which is required as the stoichiometric amount. So it will be ultimately denoted as a high efficiency system. And that by that what happens is the concentration of the unburned pollutants become close to zero. So the CO, carbon monoxide, less than 50 mg per meter cube, and the other hydrocarbons, it becomes less than 5 mg per meter cube at 11 volume percentage of oxygen. So what is the basic staged combustion? So in air staging, primary air is injected under stoichiometric. Secondary air inlet is in the reduction zone of the furnace. So as I told that two times basically air injection happens. One time is in the fuel bed and another time in the combustion chamber. Okay, so it can happen a conventional combustion. The normal air staging is done where one part is this the fuel bed in incorporation of the air, and the another part is the combustion chamber air incorporation. Okay, it is called the air staging, or you can actually divide the fuel also. So that is called the fuel staging. In fuel staging, the primary fuel is combusted to the excess air greater than one. A consecutive reduction zone is okay. So the whole fuel is divided into two parts. One part is combusted with excess air, because that there is excess air, so obviously the entire air will not be used. So there will be some excess. So the secondary consecutive reduction of zone is achieved by feeding secondary fuel. So in this way, a high amount of fuel can be combusted or incinerated in a go, in a single pass. Okay, and by feeding secondary fuel and late inlet of final secondary fuel. So two times, directly you were giving the uh, air fuel contact. Okay, one is in the directly in the fuel bed, the primary fuel, and second time in the reduction zone or in the combustion zone. So the basic reactions which happen is basically the drying when the temperature is more than 100 degrees Celsius. When the temperature goes slowly, it gets increased. So 300 degrees Celsius in presence of air, devolatilization starts to happen. By devolatilization, the volatile matter basically gets out. Then, at a further high temperature, more than 800 degrees Celsius, there is carbon gasification, which means that carbon gets in the presence of air and oxygen, it gets gasified to form the gaseous forms of carbon like CO, CO2. Example where the CO formation by gasification is shown, and by complete oxidation the CO2 is also formed. And obviously apart from carbon there is also nitrogen also is there, the hydrogen is also there, so they also form the H2O and NO. And also if there is some sulfur, also some SOx will also get formed. Okay, so the factors affecting combustion are particle size and specific gravity, ash content of your fuel or like waste, moisture content, elemental content, which is CHON, structural constituent. If it's a lignocellulosic biomass or something, so then can call that cellulose, hemicellulose, and lignin part of your waste material. Okay, and some typical advantages of this particular process are combustion is a proven low cost process. It's a highly reliable technology, relatively well understood, commercially available, common means of converting biomass to usable heat energy. Till now, till date, is the most used process, most common
Sorry,
actually.
I can't see the slides.
process to utilize or to convert the waste, to just basically combust
I
and
can't see
get
the
the heat,
slides.
and then like use that particular heat in some way or the other. Okay. Obviously, there are a lot of disadvantages of combustion. Obviously, it's not the environmentally friendly technique because it produces more indoor and outdoor air pollution than conventional heating fuels, even with the use of advanced combustion technology. Obviously, there is a fuel quality and consistency is also a factor because obviously wastes are not something which is very much uniform or homogeneous in nature. So as I talked about that the proximate analysis of sample or ultimate analysis or the composition analysis of a sample needs combustion or incineration. So it does not mean that that particular sample analysis, composition analysis will entirely, give you the idea of your actual waste material composition also, right? So that particular fuel quality and consistency is actually a challenge, and storage of fuel requires lots of space, creates a risk of fire, carbon monoxide poisoning. Already told that because of the not giving sufficient air, basically the incomplete combustion, the carbon monoxide poisoning happens. So basic flow
Devaran,
sheet of this
hello.
particular process of it covers this particular steps of pre-treatment, incineration, energy recovery, ash management, gas treatment. Uh, Simple thing which has been discussed on. Okay. In pre-treatment, there like sorting which might be carried out manual mode, automatic mode, or as a combination thereof. Obviously. So coarse mechanical sorting may not be sufficient for fluidized bed incineration. Advanced sorting processes, however, are time consuming and costly, take up a lots of space and require special precautions. Okay. Apart from sorting, homogenization is also an important thing as a part of the pre-treatment of waste. So homogenization is required for efficient incineration. The mixing is typically done by the overhead crane in the pit. So as I told that the waste is not a typically very homogeneous or uniform in nature. So homogenization as far as like to the best we can is tried to be carried out is typically done by a overhead crane as shown here. A shredder might also be used when there are large quantities of bulky waste. For fluidized bed incineration, shredding is a minimum requirement. Some example is also shown here. The refractor unit, the boilers, all those are the parts of the normal, solid waste combustion. You might also check them. There is also another lecture about incineration, which covers about the incinerator parts, their types and their working, its environmental impact, operational issues, divisions of real plant, and some case study of it. Now the screen is visible. Please let me know in chat box.
No, not visible.
So the type of incinerators, the most common types are fixed bed combustion and fluidized bed combustion. Fixed bed combustion system include the underfeed stokers and grate firings. Primary air passes through fixed bed where drying, gasification and charcoal combustion take place. Stages. Okay. Is it visible now? So please let me know. So till now, like no screen was visible, or it just happened midway.
It happened midway, sir. Earlier it was visible.
Audio is coming, right? Screen is
Yes, sir.
not
Audio is
yet
coming.
visible.
Video
I'm
is not
sharing my
visible.
screen already.
But previously it was visible, sir. Your slides were visible.
Yet it is not visible. Can somebody confirm? I have just again checked.
Not visible, sir. Not visible, sir.
Okay, I'll just check. Okay, just give me a minute. I'll just try to redo it. Okay, I think now it's visible. And
Yes, sir. Yes, sir.
thank you. And sorry, I don't know. So some technical glitch is happening. So okay, so these particular details we try to see. So just check these particular slides of this week of incineration. Okay, I don't think this will. Uh, After that was The second part of the incineration, which covers about the incinerated parts and the types of working, environmental impact, and operational issues and division of real plant. Okay. So the most common types of the combustion systems are available, which are available are fixed bed combustion and fluidized bed combustion. Fixed bed combustion system include underfeed stokers and grate firings. The primary air passes through a fixed bed where drying, gasification, charcoal combustion take place in consecutive stages. The combustible gases are burnt in a separate combustion zone using a secondary air. Among them, the one part is the underfeed stoker and the other parts are the grate firings. These are basically some constitutional parts of the fixed bed combustion. Basically the constructions. Okay. And important moving grate designs. There are some types of the grade moving grate designs. Among them are the reciprocating grate, the rocking grate system, the roller grate system, and the rotary keel system. Okay, the reciprocating grate resembles the stairs with alternating fixed or moving grate sections. The pushing action may be in the direction of west flow or in an upward motion against the rocking grate system. The pivoted or rocked grade sections produce an upward or forward motion, advancing the waste down the grade. The roller grade system, there are a series of rotating step drums or rollers agitate the waste and move it down the grade. So there are basically the examples. The reversed feed grade is just about the orientation and how you feed your material, and this moving grade positions. Okay, if it's some roller grades here, some rollers basically if you provide where some reciprocating grade type of thing are provide or some reversed feed material kind of thing are provided by which the feed is actually also provided. Okay, so basic the if we talk about the waste burning on grades, the mechanism of waste burning, so it can be actually parallel flow by a counter flow or via a center flow. So parallel flow means all the things will be happening in the same direction, the air flow and the waste material flow. The counter flow means they will be going in a cross kind of direction. This particular direction is shown here. Like one will be going in the direction, the waste is fed in this horizontal direction, and air is particularly produced in this vertical direction like that. And thus in the center, this particularly air should be going and the waste material taking the waste material from the bottom to top. Okay, so the some advantages and disadvantages of this kind of different flow patterns. So the advantages are for parallel flow, the pyrolysis gases pass through the hottest area, providing high gas burnout. For counter flow, energy transfer from the main combustion area to the drying and gasification area. Or for the center flow, it's very flexible for variable heat rate area. Okay, so accordingly, the like if you have a different categories of waste, so for a low calorific value waste, the parallel flow is more suitable. So for high calorific value waste, the counter flow is actually suitable. And central flow, the main advantage of central flow is it is or it's wide range of action. Okay, and some of the disadvantages are also shown here. Apart from the fixed bed combustion, fluidized bed combustion is another part. So in the fluidized bed combustion is basically, by the name it is very clear that the material are remain in a fluidized manner. So different from the fixed bed incinerator. Okay, you can check the basically the different types of fluidized beds also, bubbling fluidized bed, circulating fluidized bed. All those are different types, and you can check the details of that actually have been taught in this particular week lecture also. Okay. So as I told, like fluidized bed combustion is actually a very different from the fixed bed combustion. So the fixed fluidized bed combustion have the some certain advantages over the fixed bed combustion, like it is suitable or low grade fuel. The typical operating temperatures are lower than fixed bed systems. So obviously its efficiency or energy efficiency is much higher. Its combustion efficiency in fact is also much higher, and it is actually are much more scalable, or it's actually more suitable for large scale operations. Okay. Some of the examples of like heat recovery percentage and overall efficiency energy utilized, how the basically the energy is utilized, which is recovered by as a heat only, as a steam only, or to produce power only. So these kind of some things are also shown here. Okay, and some basic case study type of operating problems are also shown, like some practical from a industrial point of view also. So we can check those points also, which are actually some common problem from an industrial perspective also. Okay, and some waste incineration plants and all those some details, some examples, some case studies. What are the temperature range? What are the waste volume is like utilized, and the electricity energy efficiency? All those kind of details are also shown here. So with this, we come to some further sample problems. So dash is a waste that involves the combustion of organic substances present in the waste materials. Incineration, drying, briquetting, or all of the above. So simple, obviously incineration is a waste treatment process that involves the combustion of organic substances contained in the waste materials, already told. Combustion is the sequence of dash between substrates and oxidant, accompanied by the production of heat and conversion of chemical species. Exothermic chemical reactions, reversible chemical reaction, or irreversible chemical reactions. Okay, so yeah, it's exothermic chemical reactions. So combustion is a sequence of exothermic chemical reactions between substrates and the oxidant, accompanied by the production of heat and conversion of chemical species. Very basic kind of question. The correct sequence, the correct sequence of the steps involved in the mechanism of combustion is, we have to tell that what is the correct sequence. It's drying, pyrolysis and reduction, combustion of volatile gases and solid charge, or drying, then combustion, then pyrolysis and reduction, then first pyrolysis reduction, then drying, then combustion, or it's the So it's the first option is the correct place through three major steps. Is already told, like drying, then pyrolysis and reduction, and then finally at high temperature, the combustion of volatile gases and solid charge. Following, which of the following is not a type of fixed bed combustion system? Underfed stokers, grate firing, circulating fluidized bed, or none of the above. Yeah. So circulating fluidized bed is the correct answer because it's a part of the fluidized bed combustion. On the other hand, the fixed bed combustion have the parts like underfed stokers and grate firing. So which of the following firing combustion system? Fixed grates, moving grates, rotating grate, or vertical grates? Yeah. So vertical grades is not a obviously not a type of the grade firing. So already shown that fixed grades, moving grades, rotating grades, these are basically types. Apart from that, there are also certain types: horizontal grade, water cooling grade, dumping grades, traveling grades. But obviously, vertical grades is not a type of the grade firing combustion system. So one numerical problem: the composition of flue gas in a dry basis from an incinerator is as follows: 10.5% CO2, 5.5% O2, and the rest is nitrogen. From this data, calculate the weight ratio of hydrogen to carbon in the waste: 0.3, 0.5, zero point 0.2, or 0.1. Okay, so the correct answer is 0.2. So let's see how it comes. So you take obviously have told that it's given in a dry basis. So take about 100 moles of dry flue gas as the basis. So 10.5% is the CO2 percentage, 5.5% is the oxygen. So obviously when a dry flue gas comes, apart from CO2, O2, the rest will be the, so obviously the 84% will be the, it's told already that the flue gas is the, rest is the nitrogen. So 84% is the nitrogen. So you get that if 84 moles is the nitrogen, which means what would be the amount of oxygen is available with the in the supply, because nitrogen is inert. So obviously 84 moles was also put in the as the feed. So present in the supplied air as 79%. So it's 21% would have been the oxygen. That particular 21% was 22.33 moles. Okay. Among that, 5.5 moles was unreacted. So 22.33 minus 5.5, which is the 16.83 moles, was oxygen which was consumed. Okay. Now the CO2 is presented. About 10.5 moles CO2 is there in the product stream. So the basic equation, what is it? Is C plus O2 CO2. It obviously take it as a complete combustion, because it's told that only CO2 is there in the carbonaceous gas, right, in the product. So 10.5 moles oxygen was consumed by carbon. The rest would have been consumed by hydrogen. So the oxygen consumed by hydrogen would be 16.83 minus 10.5. Okay. Total 16.83 minus 10.5 by CO2, oxygen consumed by hydrogen. So hydrogen present in the waste, like you go the back calculation. So one oxygen mole, it reacts with 2 moles of hydrogen. So 6.33 into 2 moles is 12.66 moles of hydrogen is was present in the waste. So we just convert the moles into grams. Weight of hydrogen in waste is 12.66 into 2, which is 25.3 grams, and weight of carbon in the waste is 126. Take the ratio, 25.3 divided by 126 comes about 0.2. Okay. And with this we come to the last one. Last part is the gasification. So what was covered in the gasification? Let me just quickly open the this particular lecture. So it was covered that the of gasification reaction schemes and steps, syngas production and efficiency, and factors influencing gasification, different advantages of gasification, typical process flow sheet and utilization schemes for gasification products, syngas conditioning and cleanup, gasifier types. Until this it was covered in this particular week. The rest of the things would be covered in the next week. So simple, what is a gasification? Process that converts carbonaceous feedstocks, including biomass and wastes, into combustible gases. So when our target is basically the gases, gasification is carried out in the presence of air or steam as a feed. Okay. So what is the advantage of gasification? Because the we need to get some high value gases, some high calorific value materials as the products, such as methane, such as CO2, like that. Okay. So which is called as the the product is basically called as the syngas. So syngas can be used for various applications, including liquid fuels for production of diesel and petrol. If air is used in place of oxygen, the produced gas contains high amount of nitrogen and it is termed as okay. So uh, already told that there's usually the oxygen what is provided is usually kept as a excess portion. So if that excess, that particular oxygen is to coal ratio is more than 2.5, so the typical composition of products comes about oxygen, H2O and CO2. And obviously there are multiple reactions ongoing in a particular gasifier. Emanating conversion process will be the combustion. Okay. If that particular ratio comes within 0.68 and 2.5, the predominating conversion process would be gasification. The majority of the majority of the products will be as centered as the syngas or producer gas, with the products about CO, H2, H2O, CO2 like that. Okay, and obviously the R value, with the variation of the R value, the oxygen is to the carbon monoxide and hydrogen content decreases and water plus CO2 content gets increased with more and more oxygen. So obviously it moves towards the complete conversion of your carbonaceous waste material. And if you're giving a very low oxygen is to coal ratio, the predominating conversion process is the pyrolysis. Okay, where even some portion of solid carbon is actually left with some incomplete material which is CO and some H2. Obviously, with increase with the R, increase with the oxygen is to coal ratio, the carbon contents gradually gets decreased. So if you see the basic chemistry of gasification, so you can give the oxygen as a feed, you can give steam as a feed, and obviously your carbonaceous feedstock. So there are multiple reactions ongoing in the gasifier. So gasification with oxygen, gasification with carbon dioxide, gasification with steam, with hydrogen. So there are these kind of multiple reactions actually ongoing. Some of them are like gasification with carbon dioxide has a particular name as the Goodard reaction, which is also an endothermic reaction. To supply the heat to this endothermic reaction, we need to do or this particular exothermic kind of reactions are very important. So that part, the heat released by the exothermic reactions, like the combustion or with oxygen reactions, that particular released heat is actually used in situ in the endothermic reactions such as Boudard reaction or the steam gasification reaction like that. Okay. So if it's a syngas as a major product, you will get a high amount of CO, get a higher amount of hydrogen, and obviously a lower amount of nitrogen. And typical the heating value. Okay, but if the product is a producer gas, if the product is a producer gas, then the major component would be the nitrogen of about 50%, 45 to 55%. However, at the expense of uh, lower heating value, because getting reduced and your kind of inert material as a nitrogen is the predominant material. So some gasification reaction schemes are shown here, where feedstock will give a feedstock after some initial heating. It would create some volatile matters. Then the gasification of volatiles would be happening by this kind of generalized equation. Oxygen would be reacting with the carbonaceous volatile matter and it would produce the hydrogen and CO. and all the other, and the charge gasification will also be happening by the steam, and it would produce the CO and hydrogen. Basically the combination of them is called the syngas. Okay, and then we can like carry out the water gas shift reaction with the CO and H2, the syngas as the feed, and then produce the CO2 and H2O, which is called the water gas shift reaction, which is very important. That is why the production of CO is also not bad, but it has to be in in combination with hydrogen in a certain ratio. Then it is called as the syngas. Then it becomes important, and then it can be converted by the further reaction like water gas shift reaction. Okay, and that is the basically difference between the gasification and the combustion. Okay, the steps involved in gasification: drying, devolatilization or pyrolysis, reduction, oxidation, ash cooling. So as I told, basically the difference, the unlike incineration, in case of gasification, the volatilized gases do not get burned completely. So the entire combustion does not happen, just which happens in the case of the incineration. Okay, in gasification, gasification majorly the reduction, oxidation, this kind of or pyrolysis, this kind of reactions predominate. And obviously, due to the less oxygen supply, gasification, the charge also gets gasified. Okay, and then further, some other reactions are actually some other scientists have proposed. Okay. So one question is, Fischer-Tropsch synthesis used mainly to convert syngas into gaseous fuels, liquid fuels, producer gas, all of the above. The correct answer would be the liquid fuel. So syngas basically can be used for various applications, including liquid fuels production such as diesel and petrol through Fischer-Tropsch synthesis. In the gasification process, when air is used in place of oxygen, the produced gas contains a high amount of nitrogen, sulfur, hydrogen, oxygen. So obviously the correct answer is the nitrogen. I already told. So we'll end the session today here. I think there is again some technical glitch is happening. I'll check, and a bit of gasification part is remaining. I'll cover it in the next class altogether. Okay. Thank you for your patience.
Thank you, sir.